Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like basic optimizations for serial codes, scalar profiling, common sense optimizations, simple measures and their impacts, role of compilers, C++ optimizations. Let's get started. Slide 1. Introduction to Serial Code Optimization. Before we dive into parallel programming, it's essential to understand serial code optimization. Most programs start as single-threaded or serial, meaning they execute one instruction at a time on a single processor core. Optimizing serial code is crucial because inefficient code can slow down execution, waste resources, and increase power consumption. Serial code optimization focuses on reducing redundant operations, improving memory usage, and minimizing execution time. It involves techniques such as profiling, compiler optimizations, and logical code restructuring to enhance performance. Why do we optimize serial code? First, it significantly reduces execution time. An optimized loop might complete in seconds instead of minutes. Second, it helps in better resource utilization by making better use of CPU registers, cache, and memory. Third, optimized serial code ensures efficient energy consumption, which is especially important in embedded systems, mobile applications, and large-scale cloud computing. Example: consider a data processing program that uses a simple for loop to sum a large dataset. If the loop is optimized using vectorized operations or unrolling, the execution can be significantly faster. So, even before considering parallelism, ensuring that our serial code is efficient lays the foundation for high-performance computing. Slide 2. Scalar profiling: understanding performance bottlenecks. Now that we know why optimization is necessary, the first step in improving performance is profiling. Scalar profiling refers to analyzing a program's execution to identify performance bottlenecks. Key aspects of profiling: execution time, how long does each part of the program take? Function call frequency, are there functions being called repeatedly? If so, can they be optimized? Memory access patterns, does the program suffer from frequent cache misses? Branch prediction accuracy, do conditional statements, if-else, slow down execution? Loop performance, are there inefficient loops that can be optimized? A useful analogy: think of scalar profiling like debugging performance. If your code is running slowly, you need to figure out where the bottleneck is before making changes. Example: imagine a machine learning program where matrix operations take 90% of the runtime. Profiling tools like GNU-GProf or Intel vTune can pinpoint these areas, helping developers optimize the math functions or use hardware-accelerated libraries. Significance: profiling ensures that we focus on the most critical areas of code for improvement rather than blindly applying optimizations. Slide 3. Common sense optimizations in serial code. Once we identify slow code, the next step is applying common sense optimizations. These simple changes often provide significant speed improvements without altering program logic. Some effective optimization strategies include: 1. Minimizing redundant computations: avoid recalculating values that don't change. Store them instead. 2. Loop optimization: instead of checking conditions in every iteration, structure loops efficiently. 3. Avoiding unnecessary memory allocations: frequent allocation and deallocation of memory slow down execution. 4. Efficient data structures: choose the right structure for the job, e.g., using hashed maps instead of linear searches. 5. Reducing function calls in loops: move repeated calculations outside the loop or use inlining. 6. Replacing recursion with iteration: recursive calls consume stack space and add overhead. 7. Using constants instead of variables: constants allow compilers to optimize better. Example: consider a function that calls pow x2 inside a loop. Since pow is an expensive function call, replacing it with xx improves performance. Why does this matter? These optimizations ensure that code runs efficiently without requiring complex algorithmic changes. Slide 4. Impact of simple optimization measures. Even small optimizations in serial code can have a major impact on performance. The table here highlights how different optimization techniques transform inefficient code into optimized execution. Let's go through some of the most effective optimizations. 1. Loop unrolling before optimization. Loops iterate one step at a time, causing high overhead. After optimization, the compiler executes multiple iterations in a single step, reducing branch instructions and improving execution speed. 2. Reducing memory access before optimization. Frequent cache misses slow down performance as the CPU waits for data from RAM. After optimization, optimized memory access patterns improve cache utilization, significantly boosting speed. 3. Removing redundant code before optimization. The program performs unnecessary calculations, increasing CPU workload. After optimization, by eliminating redundant computations, we free up CPU cycles for more important tasks. 4. Efficient data structures before optimization. Using inefficient data structures, e.g., linked lists for frequent lookups, results in slow access times. After optimization, choosing hash maps or balanced trees reduces lookup time from O(n) to O(1) or O log n. 5. Inlining functions before optimization. Frequent function calls add overhead, as each call requires pushing parameters to the stack. After optimization, inlining replaces function calls with direct code execution, reducing stack operations and improving speed. Example: optimizing a nested loop by replacing unnecessary function calls with direct computations can cut execution time by 50% or more. Key takeaway: even minor optimizations significantly reduce execution time, improve CPU efficiency, and enhance memory utilization. Slide 5. Role of compilers in code optimization. Manual optimization is important, but compilers play a huge role in automating performance improvements. Compilers analyze code and apply various optimizations without modifying the logic of the program. Some key techniques include: 1. Loop unrolling. The compiler transforms a loop running one iteration at a time into a version that executes multiple iterations per cycle. 2. Inlining functions. Instead of calling a function, the compiler replaces the function call with its actual body, reducing function call overhead. 3. Dead code elimination removes unused variables and unreachable code, making the binary smaller and faster. 4. Constant folding. If a calculation can be done at compile time, the compiler replaces it with its result. Example: instead of calculating 2-3 at runtime, the compiler replaces it with 6 before execution. 5. Vectorization. Converts scalar operations into parallel vector instructions, improving speed for numerical computations. 6. Register allocation assigns frequently used variables to CPU registers, minimizing slow memory accesses. 7. Instruction reordering. Restructures instructions to maximize CPU pipeline efficiency, reducing stalls. Example: compilers like GCC, Clang, and Intel ICC optimize code automatically using flags like O2 and O3, improving performance without manual intervention. Key takeaway: compiler optimizations ensure that code runs faster, consumes fewer resources, and takes full advantage of modern hardware capabilities. Slide 6. C++ optimizations for high-performance computing. While general optimizations apply to all languages, C++ has specific optimization techniques that enhance performance. Some key strategies for optimizing C++ code include: 1. Using smart pointers, !std, unique_ptr, !std, shared_ptr, automatically manages memory to prevent leaks and improve efficiency. 2. Move semantics, !std, move, reduces unnecessary copies of objects, significantly improving execution speed. 3. Avoiding heap allocation, dynamic memory allocation, new, delete is expensive. Prefer stack-based variables where possible. 4. Using constexpr for compile time evaluation. Allows calculations to be done at compile time, reducing runtime overhead. 5. Efficient string handling, std, string underscore view instead of copying strings, use references to avoid redundant memory allocations. 6. Optimizing loops, std, vector over raw arrays. Standard containers like std, vector improve cache locality, leading to faster execution. 7. Minimizing virtual function calls, avoid excessive polymorphism where not needed, as virtual functions introduce extra processing overhead. Example. Replacing raw pointers with std, vector instead of dynamic arrays can improve performance by optimizing memory allocation and cache access. Key takeaway. Using modern C++ features helps create more efficient and maintainable high-performance applications. Slide 7. Challenges in serial code optimization. Optimizing serial code isn't always straightforward. Here are some common challenges. 1. Balancing readability and performance. Highly optimized code can become difficult to read and maintain. 2. Hardware dependencies. Some optimizations work better on certain processors but not others. 3. Compiler limitations. Not all compilers optimize code equally. A feature that works in Intel ICC may not work in GCC. 4. Debugging complexity. Optimized code is harder to debug, as instructions may be rearranged by the compiler. 5. Trade-offs between space and speed. Faster code may require more memory, so developers must find the right balance. 6. Optimization overhead. Over-optimizing can lead to diminishing returns, where additional complexity does not justify the speed gains. 7. Scalability issues. Some optimizations work well in serial execution but may not translate effectively to parallel computing. Example. Excessive loop unrolling can sometimes lead to higher memory consumption, negating performance improvements. Key takeaway. Developers must carefully balance optimization, readability, and maintainability to achieve the best performance results. Slide 8. Performance comparison. Optimized versus unoptimized code. Optimizing code leads to significant performance improvements, and the table highlights the differences between unoptimized and optimized code execution. Let's break down the improvements. 1. Execution speed. Unoptimized code runs slowly, taking longer to execute instructions. Optimized code uses better memory access patterns, loop optimizations, and compiler enhancements to run faster. 2. Memory usage. Unoptimized code uses memory inefficiently, often allocating more than required. Optimized code minimizes memory footprint by reducing unnecessary allocations and improving cache usage. 3. Loop performance. Unoptimized code high overhead due to unnecessary iterations and redundant calculations. Optimized code faster execution by applying loop unrolling, vectorization, and better indexing techniques. 4. CPU utilization. Unoptimized code underutilizes CPU resources, causing idle processing cycles. Optimized code ensures efficient CPU usage, allowing instructions to be processed consecutively without delays. Example. A simple matrix multiplication algorithm can run up to 5x faster when optimized using loop unrolling and memory-efficient access patterns. Key takeaway. Optimization enhances speed, reduces memory consumption, and improves CPU utilization, making programs more efficient. Slide 9. Future trends in code optimization. Optimization techniques continue to evolve, and the future of code optimization will integrate AI, energy efficiency, and new hardware architectures. Some key trends include: 1. AI-based code optimization. Machine learning models automatically suggest and apply performance improvements based on execution patterns. Example. Deep Code AI assists developers in writing high-performance code. 2. Just-in-time (JIT) compilation dynamically compiles and optimizes code at runtime, adapting to execution patterns. Example: JIT compilers in Java and Python improve performance dynamically. 3. Quantum computing optimizations. As quantum computers evolve, new algorithms will be optimized for quantum-friendly execution. Example: quantum algorithms like Shor's algorithm require specialized optimizations. 4. Hybrid CPU-GPU optimization. Future compilers will intelligently distribute workloads between CPUs and GPUs for better efficiency. Example: NVIDIA CUDA optimizes parallel execution for AI and graphics workloads. 5. Energy-aware compilation. New optimization techniques will focus on power efficiency, balancing speed and energy consumption. Example: ARM processors use energy-efficient optimizations for mobile devices. Significance: the future of optimization will be AI-driven, hardware-aware, and focused on energy efficiency, ensuring better performance for next-generation applications.